You might have heard of Mergesort before, but basically it's another sorting algorithm. So if I have an array, let's say 7, 4, 1, 5, 3. Okay, let's actually make it look like an array. Okay, so we want to sort this array, and we want to use merge sort. What merge sort will do, it's a divide and conquer algorithm. So what we will do is split the array in half. And again, I've chosen an odd-sized array, and your implementation has to handle that. So what we'll do is then we create 2 smaller arrays, 4 and 7, and 1, 5, and 3. Okay, and the algorithm then looks at the smaller and says, is this greater than size 1? Yes, it is. Well, then we can split again. Again, I'm going to split like so. So then we will have an array of size 1, which just has 1 element, and an array of size 1, which just has 1 element. Meanwhile, on the other side, we have another 2 arrays. So we have, that results in an array of size 1. This results in an array of size 2. Okay, we're finished in all of these, but let's complete the final split here. So this is still size 2. So we create smaller arrays, and that's then 5, and that is 3. Okay. So this whole phase of the algorithm is where we are dividing the problem up. Okay. And we're doing this via recursion. Okay. Once we have essentially reached this base case where all of these are size 1, what we want to do is to start merging all these arrays together. And we will merge these 2 arrays that can become size 1. So let's maybe use a different color for the merging part. Okay, so if we merge these 2 together, the way a merge function works is it tries to get them in the right order. So it looks at the first element of this array, first element of this array, says who's the smaller value, 4 is a smaller value. So we put 4 and then 7. Goes like so. Okay. Then this branch we have here, do the merge on 5 and 3, and again 5 is greater than 3, so we swap those around. So we get an array like that, and then we need to finish this branch with the array of size 1, and these, and a merge works on different sized arrays. So we just look at the first element of this, the first element of this, and the first element is smaller in the first array. So we then get 1, 3, and 5. Okay, and then now we can merge, well, not like that. I'll just hit the zoom rather normally. So if I can find my way back to that, okay, so we do the final merge, and I'm going to be picky and use blue. Okay, so then we will look at the first element, 4 and 1. Okay, 1 is smaller. Then we'll look at the next element, 4 and 3. 3 is smaller. Then we'll look at 4 and 5. 4 is smaller. Then we'll look at 7 and 5. 5 is smaller, then there's nothing else to look at. We've exhausted that array, so we can put 7 in. Okay. And double check we have a sorted array. Okay. So this part is the merge part. Okay, so that's kind of the high-level view of how the algorithm works. To get a pseudocode with this will not be the most complete merge sort algorithm in the world, but it will contain at least the essence. We have an array, and we need a low pointer and a high pointer in the array. Okay, so first thing we need to, we check if low has went past high, then we can simply return. What this means is that our pointers have crossed and we have arrays of size 1. Okay, so they're now small enough to be a base case. Otherwise, then we need to do a couple of things. I'm not going to write code for it, but we want to find a midpoint. Again, just get the midpoint. And we also want to create subarrays. Okay, it's worth noting this is one of the costly parts of merge sort, because in a naive implementation, you actually create a lot of auxiliary structures to store the sub-results in. So you're creating these small arrays all the time. So that can be time or no, space consuming, not time consuming, but space consuming. Okay, once we've done that, we can then recursively call merge sort on the, let's say the lower copy subarray is called the low part, and we go from the low to the midpoint. Okay, then that deals with the left-hand side. So in our example, that would be 7 and 4. Then we need to call merge sort on the upper. I'll just call this subarray a high, and that will be from the midpoint to high. It could be like +1 on that, but again, it doesn't really matter. Okay, so that will then recursively create a second recursive branch, which will start dealing with the upper part of the array. And then to conclude this, we call a merge function. Okay, and there's probably a lot more details and pointers and stuff need to be included in the arrays or the parameters here. But basically, we take those two subarrays and we merge them together. And again, a merge function is like a helper function here. It actually does a lot of the work. So if we have two arrays, 3 and 5. So let's say A low and A high was 1, 2, 4, and 3, 5, 4. If we call a merge on these two arrays, what we're going to do is we're going to have a pointer looking at the first element here, pointer looking at the first element here, and then say which is the smaller. So 1 is the smallest one. Okay. Then we keep the pointer in the second array where it is, but we move in the first array. So now we compare 2 to 3, and 2 is a smaller value. Move the pointer along one more time in this array, and 4 versus 3. 3 is a smaller value. Move the pointer along here, and then it's 4 versus 5. 4 is a smaller value, and we move the pointer along. There's no other values, so we conclude there. Now we can put 5 in there, and the pointer moves along, and there's nothing else to merge. Okay, so although I'm not going to go through the merge algorithm in code or pseudocode, it roughly achieves that. What's worth noticing is I had 7 elements here, and there was 7 operations. So one of the things to note about the merge sort algorithm that this will have a linear cost. Okay. But then we have these 2 recursive branches. in the calls. Okay, so it's a lot of setup first of all, but what we can then do is let's maybe highlight these things. Okay, so there's two recursive calls, and then there is the merge. Okay, so if I go and try to create a recurrence for this, okay, so let's say I'll just call the function t of n, and the n would be the size of the array. Okay, so simplify that time. Okay, the way I could write this recurrence is, well, there's an if else here. Okay, so there's two branches. We can either go to the base case, or we can go and break down the problem. There's two merge sorts being called, one after the other. Okay, so then we can say that there's going to be two calls here. Okay, and then the problem size down here, if I can use a different color. Okay, we find the midpoint. Okay, so this is going to be half the problem size. So then we simply say, okay, this is going to be n over 2. Okay, so that's captured the recursive part of the algorithm. Now we need to deal with the merge part. Okay, and simply here, well, like I hopefully illustrated, this isn't a single operation. This has to merge two arrays together, and so it has a linear cost, which is basically the total of these two arrays. Okay, so then this becomes n. Okay, and the recursive case we can skip over it here. I think we have enough of the information we need. Okay, so we have the recursive part. We have the, oops, wrong color. We have the merge part, and we have the splitting of the problem as well. Okay, so now we have basically what A should be 2, and strong regrets about using colors because it's hard to remember. Okay, and then C, yellow for that. Okay, in this case, remember C is like this. So to get n, C would have to be 1. So n to the power 1 is n. Okay, so now that we have those coefficients, we can then solve the inequalities. So we take, okay, just note while the master theorem, we want to say, well, what is e to the power of c? Okay, that equals 2 to the power of 1, and then we should have, we can see that A is equal to 2. Okay, so we need to go back and find the right slide. Okay, so then A was equal to B to the power C. So A was 2 equals B to the 2 to the power 1, which is equal to 2. So we have the form of, we go, whoops, go back here. So of n to the c log n. Okay, and then we just simply substitute c in, which is 1. So then we get the notion that the time complexity of Mergesort is linear arithmetic, or n log n. Okay, and hopefully if we scroll back, we can sort of see how that happens. We have this recursive part that divides the problem in 2. Okay, so we can see where we're getting log n from. So depending on the size of the array, we'll have that many cuts until we get down to the base case. And then we have this merge part where we basically have a linear cost of merging all these elements back together again. So we get our estimate of the time complexity for merge sort. So even though we have probably not seen this algorithm before, what I've tried to show there is going from the pseudocode for a recursive algorithm that's different from binary search. So again, binary search just had a single recursive branch, but now we can see an algorithm that had two recursive branches, and it also had a linear cost of the effort each time. Binary search only had the effort of making a guess. Is this the right answer? Yes or no? But with merge sort, each time we have this recursive branch, we also need to merge those subarrays back together again. Okay, and that gives us still pretty good performance if we think about the other sorting algorithms, insertion sort, selection sort, having quadratic performance. We've now got a sorting algorithm using recursion that has a slightly worse than linear time complexity, which is actually super good for the problem. Okay, hope that was useful. And shame it didn't fit into the lecture, but now that I actually just worked through it, it actually was quite a long example. Okay, but I hope it made sense.